right. Thanks, everyone. It's a pleasure to be here. Thanks for the invitation. So I'm going to talk about prismatic cohomology relative delta rings today. And I've not been here last week, but I take it you've learned a bit about prismatic cohomology from Johannes. So in particular, Johannes explained two flavors of prismatic cohomology. So, prismatic cohomology comes in two flavors. The first of which is relative prismatic cohomology. As defined by Butt and Scholze. And this takes the following format. Its input consists of some A, and A is a prism. So it's a pair of a delta ring, that's the A, and some ideal I in A with some properties, which we call a distinguished ideal. And an A mod I algebra R. And of course you can also say this in a non-affine way. You can put general A mod I schemes there. The whole thing will have Zariski descent. We'll stay affine in this talk. But everything I say will of course also work for schemes. So that's relative prismatic cohomology, and somehow crucially uses this prism structure. There's also a version which just does not have a base prism. It's absolute prismatic cohomology. And this is coming out of work by Butt, Morrow, Scholze. This is the paper commonly referred to as BMS2, where they construct this theory out of a relationship to variants of THH that I'm going to talk about in a second. And so that's originating in homotopy theory, but of course it also has been recast in a purely algebraic definition by Butt-Lurie in their absolute prismatic cohomology paper. And they somehow define that in terms of the relative version. And this has the format that its input is just a ring R, commutative ring R. And I guess depending on your taste, you could put either like P complete as a condition inside, or observe that if you try to define these for non-P complete things, then it just factors through P completion. And if you have something absolute and something relative, you somehow want to view the absolute thing as relative something particularly easy, right? Like cohomology is relative to the empty like absolute cohomology of a topological space is relative to the empty subspace, for example. But here, it doesn't really make sense to write prism R relative ZP. This only makes sense if R is an FP algebra, right? Because in this relative version, we're asking to have a prism structure on A. So that needs to be some ideal that's compatible with the delta ring structure in a certain way. It needs to be locally principal and generated by some element delta of which is a unit. And you can work out that on ZP, the only ideal that makes sense is the ideal generated by P. And so since this only is defined for A mod I algebras, This here, that only makes sense in the case of FP algebras. However, in that case, it does agree with absolute prismatic cohomology. And so what I want to explain to you today is that there is a version, a common generalization of these two things that just makes sense in general for a pair of any delta ring A. You don't need to fix a prism structure, and any algebra over A. You don't have to be an algebra over some nice quotient of A. So that's what I mean by prismatic cohomology relative delta rings. We are working relative, but we're not working relative a prism. We're working relative an arbitrary delta ring. And it will turn out that this thing relative a prism will actually just factor through the functor that just forgets that you had a prism. So in that sense, this relative thing that I'm going to explain today will generalize that. And it will also generalize absolute prismatic cohomology, because then in this relative delta ring setting, you can always write relative ZP, and that will just always be absolute prismatic cohomology. So I think it's a quite satisfying explanation for how these two things are related.
So is this prismatic cohomology independent of the ideal?
Well, not a priori, but that's part of what I'm saying is that if there are different ways you could choose a prism structure on A here, such that R is an A mod I algebra. So if there are different ideals, like distinguished ideals in the kernel of the map from A to R, then what we observe is that it doesn't matter which prism structure you chose. But it does matter in the definition of relative prismatic cohomology. So it's somehow an extra observation that it's independent of that choice. All right. And maybe before I try to give some kind of definition for this, let me discuss with you several pieces of evidence that you could believe that it doesn't matter to choose a prism structure on the base. So the first evidence, and in my opinion the strongest one, comes from homotopy theory. I want to explain a little bit what I mentioned over there, that absolute prismatic cohomology arises from studying THH and variants thereof. So let me tell you what that is. So for a commutative ring, we may view this as a ring spectrum, right? I mean, this is a Z algebra, but then we can also view it as a discrete spectrum, and then it's an algebra over the sphere spectrum. And you can form Hochschild homology relative the sphere spectrum. That's what's commonly called THH. So you can also write this by some cyclic bar construction, or by forming some enveloping algebra R tensor over S with R, and then tensoring R with itself over that. Right? R is an RR bimodule. So I'm dropping the ops here because R is commutative. But of course, there's a version for non-commutative rings as well, and then you have to be a bit careful about the ops. And this carries an action by the circle group, which comes essentially from some kind of trace symmetry in this construction. And one has refinements of THH, which are obtained by taking fixed points with respect to the circle action. So can take just the homotopy fixed points of this S1 action. And you can also take the Tate construction. And these are like analogs of what people did in the setting of Hochschild homology with HC minus and HP. So they're called TC minus and TP. And so in general, this is difficult to compute, but one thing you can observe is that if THH is concentrated in even degrees, the homotopy groups of this spectrum live in even degrees, then the homotopy fixed point and Tate spectral sequences that you always have that converge against homotopy groups of the homotopy fixed points and the Tate construction, they both degenerate. Let me draw a very qualitative picture of how that looks like. So in the homotopy fixed point spectral sequence, you would have the cohomology of the circle group with coefficients in the homotopy groups of THH. The homotopy groups of THH are some stuff that's somehow concentrated in even degrees here. Let me just draw dots and think of these as living in even degrees. And there's nothing in between. And then the cohomology of the circle group also lives in even degrees, right? It's like the cohomology of CP infinity. So you have this picture here where every dot lives in even total degree.
Now you have homological notation in the spectral sequence.
This is homological Serre grading, yes. So you would, yes, it's homological. That's why the cohomology of the circle group goes off to the left. And you would see pi 0 of the homotopy fixed points as an extension of the terms on this diagonal. And pi 2 as an extension of the terms on this diagonal, and so on. And so this degenerates, and it exhibits whatever the homotopy groups of this TC minus are as some infinite extension of things that are various homotopy groups of THH, right? Like the circle, the cohomology of the circle group is just polynomial in one generator. So in every row, all the terms agree. And so this pi 0 TC minus, it's some complicated extension of THH0, THH2, THH4, and so on. And this is also some complicated extension of groups like this, but maybe a different one. So what happens with the Tate construction instead? Well, Tate cohomology is somehow like a periodic version of cohomology in many cases, and that also applies to the circle group. So in that case, you get the same picture, but lives on the entire upper half plane. And again, you have a dot only in even, every dot lives in even degrees. There's no space for differentials, and this degenerates. And now here you would see pi 0 of TP and pi 2 of TP, and so on, as possibly complicated extensions of the homotopy groups of THH. And so one thing you can notice is there's always a canonical map from homotopy fixed points to Tate, and on that picture, that does what you would think. It just takes that part into that part. And so the fact that the spectral sequence degenerates and everything is just an extension of those groups, in particular tells you that pi 2 of TC1, pi 2 of TC minus is just a certain subgroup of pi 2 of TP, namely the one picking up everything in this extension except for the THH0. And and so on. And you also see that pi 0 of Tc minus agrees with Tp.
Does one have S1 action or possibly called truncations?
Yes.
Yeah, okay, so one can have enough convergence. I mean, the construction of the spectral sequence decides that you have enough convergence to justify this. That is you have a complete and separated filtration on the abutment to the associated ray that is given by, in this case.
Yes, so in general, this Tate spectral sequence is what's called conditionally convergent, but in the case of where it's like an upper half plane spectral sequence and there are only finitely many differentials, that means that it's strongly convergent. So the filtration you have on the homotopy groups of the Tate construction is really complete. Yeah. So what this tells you is that somehow, if you knew the homotopy groups of Tp and this filtration, then you would also know the homotopy groups of Tc minus, right? So you could read them off. For example, pi 2 of Tc minus is a subgroup of pi 2 of Tp, namely the one that's just the part starting at this stage of the filtration that the spectral sequence gives you. And so one sees in particular that these homotopy groups of Tp, pi 2i of Tp, come with a canonical filtration. And that's the filtration that's called Nygaard filtration on the side of prismatic cohomology. So let's call it n bigger equals star. It's just the filtration that you get from the spectral sequence. And it also knows about Tc minus. N bigger equal I of Tp2i is Tc minus 2i. And if you see this, that somehow in certain cases it seems like these homotopy groups of Tp are algebraically quite nice behaved. They're really like concentrated in even degrees, and you have some filtration that also tells you what Tc minus is and so on. Then one thing you could try to actually describe is to actually describe that algebraically. And so in this case, it turns out that if you try to turn this into an algebraic description hard enough, you discover a prismatic cohomology. Turns out that Tp2i of R, in a certain generality, namely if R is quasi-regular semi-perfectoid, that's a condition that guarantees that THH is actually concentrated in even degrees. It turns out that this is Nygaard completed prismatic cohomology, absolute prismatic cohomology. And this is with Breuil-Kissin twist I, because it turns out these, even though the E2 page of the spectral sequence is periodic, the homotopy groups of Tp are actually not periodic. They're somehow only weakly periodic in the sense that pi 2 is some invertible module that somehow the others are tensor powers of. So there's some kind of twist involved, and that's what the Breuil-Kissin twist does on that side.
So in the construction of Hochschild, you took tensor product, but do you have to periodically complete also or not? In setup?
That's a good point. So you can do this integrally, but to get something that's related to prismatic cohomology, you want to p-adically complete. So everything here is p-adically complete.
And this commutes with fixed points?
It does.
Yes.
Yes. So Okay, so you have to complete once, either inside or outside. Okay.
Right. Right. Okay, so this is how absolute prismatic cohomology arises from studying these things. And now, this was in fact the first incarnation of prismatic cohomology, right? That like only later Bud Scholze figured out how to do this in an algebraic way. But in this world of THH, we also have relative variance. And let me give you one example for a very useful relative version. So there is something that looks like a polynomial algebra over the sphere spectrum, which you can just write as a joint Z, but it's not defined as the free commutative ring spectrum. That would look different. It's really defined just like an ordinary polynomial algebra as a sum over all natural numbers, right? So this is really, in a sense, a free module on monomials in the Z. And you can also look at relative versions of Tc minus and Tp, where you just work relative this as a joint Z. So you have to specify some map from S adjoint Z to R, but since R is discrete, that just amounts to saying where the element Z has to go to. And then you can just define that just in the same way as over there as relative THH. So that's the same Hochschild homology construction, just replace S by S adjoint Z. And then take the Tate construction. And I guess I want to again p-complete in order for this to have any relation to prismatic cohomology. And BMS also observe that this relative version admits some prismatic interpretation. So they observe that for OK, some p-adic number ring, some like, rings of integers in some finite extension of QP. You can always write this as Witt vectors on some finite field, adjoint Z, modulo some Eisenstein polynomial. And any OK algebra R, they observe that TP R relative SC can be described or can be related to prismatic cohomology of R relative this ring WK adjoint Z. And I'm a bit vague here because earlier here I had this additional condition floating around that THH lives in even degrees, and then I said in that case you can really describe the homotopy groups in terms of prismatic cohomology. For general rings there's still a version of this comparison statement, but then you have to, instead of talking about the homotopy groups, introduce some filtration on TP that in this even case coincides with the Postnikov filtration. And then, so the general comparison statement is there is a filtration on TP whose associated gradient is equivalent to prismatic cohomology with these twists. And they prove a similar statement for this. And by prove, I mean in BMS2, they prove that there is a thing that canonically agrees with this, and then that's later identified with this relative prismatic cohomology once that has been set up. So, and to be precise here, what's compared to this is actually, again, Nygaard completed and Frobenius twisted. Somehow that didn't come up in the absolute case. We'll see why, but the takeaway is there's some version of prismatic cohomology that describes this here. But what I want you to observe is here we had to choose somehow an Eisenstein polynomial, right? For this statement, we need to talk about an OK algebra R. So we need to choose this ring OK, and in particular, we need to choose some Eisenstein polynomial. And TP just doesn't care, right? You can plug in any ring with any choice of element here, and you get a map from S adjoint Z that takes Z to that element, and you can look at relative TP. So this side here exists in much greater generality than the right-hand side. The right-hand side is somehow prejudiced on a choice of Eisenstein polynomial, and also on the choice of finite field K. The left-hand side just you didn't input that on the left-hand side. Somehow, it still seems to include those things.
No, but Z, you have to specify how Z goes to R. So Z goes to OK is exactly a choice of uniformizer in OK, which...
That is true. Yes, that's a good point. So I have to choose an element, and there are many examples of R where that already determines everything. For example, if R is of the form OK itself, then if I specify some map that takes Z to a uniformizer, then I also know about the ideal generated by the Eisenstein polynomial, right? It's just the kernel, at least if I replace the ZP here by some Witt vectors. But there are also examples of rings where you could choose multiple OKs, right? Take any FP algebra or any algebra over little k, that can be made an algebra into an algebra over multiple different of these OKs. And so TP seems to hint at the fact that we don't really need to choose the OK, that there's some more canonical description of the right-hand side. And in a sense that maybe sounds more like a philosophical type of question. After all, if we have that theory, in any practical case that we want to compute, we might just choose a prism structure and be done with it. But there's another thing also observed first in homotopy theory, which is...
Sorry, can I ask something before you go on? By S, does that mean you have something in degree, so it's a free, but it is a free infinity algebra in one generator in degree 2?
No, it's not that. It's what's written on the right-hand side. It's a sum over, it's a direct sum of just copies of S in degree 0 indexed over the natural numbers.
Ah, okay.
It's just a monoidal ring of N.
Yes, you could write this as S adjoint the natural numbers. As a monoid ring. It's not free. It's pi 0 is free on a generator in degree 0 as a commutative ring, but the thing itself is not free as an E infinity.
Okay.
So what is the free thing? When you adjoin Z, what you...
The free thing, the free E infinity ring over the sphere on one generator Z, it looks like a sum over all natural numbers of S and then homotopy orbit sigma n. So somehow the fact that in the free thing there are also witnesses for the fact that Z commutes with itself gives you some higher homotopy groups and so on.
So this is what? This is S homotopy, the homotopy co-limit of...
Yes, another way to write this is as something like sigma infinity of B sigma n.
Plus.
Plus, yes.
I was thinking about it and then I did exactly the wrong thing.
Sigma infinity, and how does this map to, the free thing should map to your thing, so how does it map?
It maps by, on each summand, by the augmentation map, right? This is sigma infinity plus of the point, and there's a map from B sigma n to the point.
Right, but on the level of homotopy orbits, it's not...
So this guy, for example, it has the right pi 0. Pi 0 of homotopy orbits are just z. But it does also have some pi 1, namely the abelianization of sigma n. And then it also has higher homotopy groups. And you're essentially just dropping all of that. So you could think about this guy as somehow the free thing where z strictly commutes with itself, because you've somehow removed all these braidings.
Like, could you make sense of the map just coming from the finite set category down to the natural number where, like the finite set category, I'm only thinking allowing automorphism between the natural numbers, so then it's just the map from finite set onto the natural number where I forget the map.
Yes, that's a way to say the same thing in on the level of categories, yes. Okay, so, but this working relative a polynomial ring is the thing that behaves better algebraically, because that polynomial ring is in a sense flat over the sphere and the free guy isn't. And as a final observation, why we might want some kind of version of prismatic cohomology that doesn't force you to pick an Eisenstein polynomial in the beginning, observe that relative TP was also used in a pretty cool way by Wang and Liu. They observe that the cosimplicial diagram where you have absolute TP, this maps to relative TP. And then you can map in two different ways to TP relative a polynomial ring in two variables, defined just like over there. You just replace the n by n cross n. And then so on. You take all the elements z to the same element of R, take z0 to your uniformizer, for example, and z1 to the uniformizer. So that's a diagram you can write down. And they observe that this is a limit diagram. And now, if you want to make sense of the same thing in prismatic cohomology, right? You would start by doing something like prism R. And then here you want to put the relative thing, which in BMS2 should be this Witt vector thing. That's good, right? Okay, we have a map like this. And now for the next guy, you maybe want to put something like prismatic cohomology relative a power series ring in two variables over Witt vectors. Take both of the power series variables to the uniformizer of R, and you can make sense of all of this so far, right? This is absolute prismatic cohomology. This is relative prismatic cohomology, relative a prism. We pick the Eisenstein polynomial in here as the generator of this ideal I. And then here, you suddenly have to make a choice. There are multiple prism structures you could choose. You could choose E of Z0. That's a perfectly fine distinguished element that's taken to 0 in R. You could also take E Z1. And suddenly, you're a little worried, right? Because if these lead to different answers, then that's maybe a bad choice to make. But you could pick one, right? Let's say we pick the first one, EZ0. Then what should the first map here be? Well, easy. That's just the map that takes Z to Z0. And it takes the Eisenstein polynomial, E of Z, to the Eisenstein polynomial, E of Z0. So that actually comes from a map of prisms. That's good. That should induce a map on relative prismatic cohomology. But then finally you run into a problem. Because this other map, that will take E of Z to E of Z1. And if you've made this into a prism by choosing E of Z0, then that's not a map of prisms anymore. So if you want this, which somehow topology tells you should exist, right? In topology you could just do this. But on this side you can't, because you have to choose this prism structure and you can't make the maps compatible with the chosen prism structures all at the same time. So what you would need to write down this diagram is some kind of statement that it doesn't matter which of the two you pick, that there's a canonical isomorphism between these two different things. And then, of course, you have the same problem going on, which could be solved in the same way. So this was evidence 1, and I think it's the strongest piece of evidence that something like this should exist. But of course, there's also algebraic reasons why what I just said, choosing different distinguished elements, shouldn't make a difference on the level of prismatic cohomology. And let us also look at this. So how was relative prismatic cohomology defined? It was defined through a prismatic site for R and A mod I algebra. The prismatic site that prismatic cohomology was defined over consists of squares A, R, B, B mod J, where B is a prism with the ideal J, and A to B is a map of prisms. So what does that mean? It needs to be a map of delta rings, and it needs to take the ideal I that defines the prism structure on A into the ideal J in B. And by into, I really mean that the ideal on B should be base changed from I. And now there's a cool observation, which is that you wouldn't need to ask for that. So if we only ask for A to be a delta ring map, no compatibility with the ideals whatsoever, then let's maybe call this map F. F of I is still contained in J, right? Just because the diagram commutes, and we did ask for R to be an A mod I algebra. So I is in the kernel of that map, so it needs to be mapped in the kernel of that map. But there's a cool lemma on these distinguished ideals. Just uses some clever tricks about delta rings. Johannes mentioned that he talked about this. But if you don't remember, don't worry. The statement is just that automatically J is equivalent to the base change from A to B, maybe completed base change. And in other words, A to B is a map of prisms. So some weird magic of delta rings just forces any map of delta rings here to be a map of prisms, as long as this R is really an A mod I algebra, as long as this I is in the kernel here. But what this tells me already is that if I could have chosen, say I forget the I, if I then just pick any I in the kernel which does define a prism structure, this lemma tells me that any diagram with a delta ring map here gives me an object of the relative prismatic site. So what this tells me is that for different choices of prism structures in the kernel here, the prismatic sites canonically agree. And more generally, I could define a relative prismatic site by never talking about prism structures on A and not asking that R is an A mod I algebra. I could just say, okay, for a pair of a ring R, of a delta ring A and an A algebra R, I could just define a prismatic site as consisting of squares like this, such that the map up here is a map of delta rings. And whether that definition makes sense, we don't know at this point in the talk, but at least this would give the right thing in the prismatic case, in the case where there is an ideal in the kernel that defines a prism structure on A.
So what you have written there, so as far as I remember, so the map of prism was just a map preserving the ideal and the delta structure. Mm-hmm. So the preservation of the ideal is automatic. So there was a lemma when in the basic signal prism that f of I is equal to, that I generate J, but this is a map of prism. You don't need it to know that you have a map of. The definition of a map of prisms was already okay. It's not.
You could define it in two different ways, is what I'm saying. You could define it in the stronger way that you really ask the prism structure on B to be base changed from A, but what's proven in Bad Scholze is that it actually follows from this weaker condition that F is just taken into I. So what this tells us that somehow this prismatic site really doesn't depend on the choice of prism structure as long as there exists one. And you could define this more generally if you just don't have a prism structure. For example, if A is just ZP, the initial P-complete ring, then if you just look at diagrams like this, where this is any delta ring map, there's no data whatsoever, so then this recovers the absolute prismatic site. Okay, so and you can actually turn this into a definition. So just for a delta pair, a pair of a ring and a delta ring and an algebra over that, you can just write down this site, and then under suitable quasi-symptomicity assumptions, this site does actually compute something with the desired properties. So let me give you a definition of what a delta pair is. A delta pair is a pair of a delta ring A and an A algebra R. And then what I just said, that's our main theorem, is that there's a well-behaved...
Would you lower the cup more, please?
Like this. So there is a well-behaved notion of prismatic cohomology of such delta pairs. And let me just give you a bunch of properties this satisfies. Oops. So So there exists a functor from delta pairs to complete filtered objects in the derived category, in the p-complete derived category. With the following properties. If A is ZP, then it agrees with prismatic cohomology, absolute prismatic cohomology, with the Hodge-Tate filtration. Absolute prismatic cohomology always comes with a complete filtration, and that's somehow built into this theory. And in the absolute case, it's the same filtration. Secondly, for any ideal in A in the kernel of A to R, which defines a prism structure on A. So this might sometimes exist, sometimes not, and there might be multiple ones if they exist. In that case, the prismatic cohomology relative delta rings agrees with relative prismatic cohomology. So in the sense of Bad Scholze, so relative to the prism A, I. And in that case, the filtration, this Hodge-Tate filtration, is the I-adic filtration.
Excuse me?
Yeah.
In the first statement, the left-hand side is your functor, right? So
yes. Yes. Yeah. Somehow this theorem shows that there is no notational clash, but in stating the theorem, maybe one should write something else. Yeah. Yeah, maybe to alleviate some of the possible confusion. We're of course calling that functor prism lower blank relative blank.
So the R is fixed?
No. Delta, we have this notion of delta pairs, consists of an A and an R. And a morphism of such is a delta ring map on the delta rings and a map on the rings such that the diagram commutes. And the thing is functorial in that. It's functorial both in the base delta ring and in the ring you plug in.
We didn't ask in the differential delta pair we have this A to R has a kernel I.
No, you don't have. So 2, it doesn't need to be surjective. It doesn't need to have a prism structure in the kernel or so. It's any map from a delta ring to a ring. I'm just saying that if there is any admissible prism structure, any prism structure on A such that the R is an A mod I algebra, then it agrees with the Bad Scholze thing.
So this is a prismatic cohomology of the structure sheet of the
this can be defined under extra like quasi-symptomicity conditions in terms of this prismatic site where you just forget about the prism structure of A, yes. And then the structure sheaf would be the factor that just takes such a square to B. So this is the two properties, how it compares to absolute and relative prismatic cohomology. And then it has some kind of invariance properties. For example, if you work relative A and relative some A prime, where A to A prime is relatively perfect, so both mapping to R, then they're the same. And also has some base change properties. Prismatic cohomology R relative A. If I just tensor that over A with any other delta ring B and complete with respect to the filtration I have here already, right? This is a filtered object, then it agrees with the
I'm sorry.
Yeah.
What's relatively perfect?
It's the easiest way of saying that. The square where you have the Frobenius maps as a push out. So in other words, the relative Frobenius map from the thing, yeah, this is a push out.
So in 4, you take R tensor AB is a derived tensor product?
Yes. Yes.
But then you didn't say that you're defining for derived thing.
Yes.
How define delta rings in the derived setup? Or?
Yes. Okay. So I was trying to get around that. This is something that you can define for delta pairs, but it's also left Kahn extended. And so you can extend it to animated delta pairs. And so you can ask for either the ring or both to be animated. And if this tensor product has no higher Tor terms, then this holds as I wrote, but in general, this needs to be this animated version.
And when you speak about relative prismatic cohomology, it is the left Kahn extension version of it that we discussed, the one that has better properties.
Yes,
okay.
the derived version.
But this is slightly subtle, right? Because you end with in the category of completely filtered objects. I mean, you do the.
Yes, so this is left Kahn extended as a functor to complete filtered objects. So you take a colimit and then you complete again. The filtration needs to be part of the datum for this to make sense. Right, and then.
Sorry, Achim, is it clear that this R tensor AB has a delta ring structure?
No, that's just a ring.
Oh, that one's the ring. Okay, I got confused by the notation. So A to B is a map of delta rings here. Yeah. Okay.
Yes.
Yeah. Okay.
Yes. And then this is still a delta pair. Okay, and then it. Let me abbreviate here a bit. It's left Kahn extended, and it has like certain descent properties.
Left Kahn extended, you mean from formally smooth algebras or something?
From free delta pairs, right? Now that we don't have to fix a prism structure anymore, one particular case that you can apply this to is just A is a free delta ring on finitely many generators, and R is some polynomial algebra over that, and it's even left Kahn extended from that. That's very much not the prismatic case. This will look more like absolute prismatic cohomology, but it's something you can do.
Okay, but if you fix the base delta ring and you just consider algebras over it, so then it is left Kahn extended from smooth or no, from the polynomial.
Yes, if you fix the base delta ring, then it's also left Kahn extended from polynomial A algebras.
And it commutes with filtered colimits or even okay.
Sifted. Yes.
Sifted.
Commutes with sifted colimits. Maybe I should have written that instead. Commutes with sifted colimits. And then this is just prismatic cohomology with like no decorations, but of course, and it would take me probably one more talk just writing all of the structure down, but the other structure like Breuil-Kissen twists and Nygaard filtration on the Frobenius twist. So you base change this along A, along the Frobenius on A. This also generalizes. So it has basically all of the properties that you would expect from absolute prismatic cohomology. Some of the stuff that happens in relative prismatic cohomology does actually depend on the choice of the ideal, notably the conjugate filtration, if you know what that is. But everything that you have in absolute prismatic cohomology you also have for these delta pairs. And let me maybe finish by stating a nice comparison result to this topological setting, to TP and so on. So given a flat S algebra, so something like this S adjoint Z from earlier. Let's just call this S lower A, and let's call pi 0 of it A. So I'm thinking of this SA as some kind of flat lift of this ring A to the sphere. Then let's maybe say P complete here. Then A inherits a delta ring structure. That's not the main part of the theorem. That's something that I learned from Thomas. It goes back to these properties of the Tate-valued Frobenius. But so for any of these S adjoint Z guys or so, there is already a delta ring structure on its pi 0. This is not extra structure you have to specify. And now for...
So what does it mean flat in this context? Because
flat means pi 0 SA is P completely flat over ZP. And the higher homotopy groups are just base changed from pi 0. So I have to write pi 0 SA tensor over ZP with pi n of S. That's exactly the property that you want here that, for example, the free infinity algebra did not have.
Right now, I'm not sure whether you need to P completely.
It's finally generated.
The homotopy groups are finite. So there is such a delta ring structure, and now what we construct is there is a natural in A algebras R filtration on TP R relative SA with isomorphisms between the ith graded and this prismatic cohomology relative delta rings, Frobenius twisted and Breuil-Kissin twisted and shifted by 2i. So this is the same type of statement that, yes, and Nygaard completed. So this is the same type of statement that BMS2 establishes in the absolute case, where you just have the p-complete sphere here, and in the in this Breuil-Kissin case, where you work relative with vectors adjoint z. And now that we have this prismatic cohomology relative delta rings, this makes sense in this generality, and it's actually true. And so in particular, this sheds light on some things that I think so far were not completely understood. So let me maybe finish by that. Corollary, if this prismatic cohomology is discrete, so this holds in some kind of relatively quasi-regular semi-perfectoid setting, for example, the cyclotomic Frobenius on TP0 is actually a Frobenius lift. It's kind of mysterious what the cyclotomic Frobenius has to do with Frobenius lifts in general. And that's like in the absolute comparison result, that's kind of the hardest step. If you knew that beforehand, then you would already have a delta ring structure on TP0 and you would get a map from universal properties. That's the hardest step to prove that in the special case where you just work relative the sphere. And it's so far, I think, still open to find a more direct argument for why TP0 sometimes has this property that the Frobenius, the cyclotomic Frobenius mod P is really the usual Frobenius. But this here gives a nice explanation for it. It holds exactly if the, or it holds in particular if the prismatic cohomology is discrete.
So Achim, so is this relative Frobenius, the cyclotomic Frobenius always defined in this relative situation for such algebras, or?
I think so.
Yes, SA is a cyclotomic base.
Oh.
I think that relates to this statement here. It comes from the fact that the Tate construction is just the p completion. So like that's also the reason for this here.
And are you going to address the question of which delta rings admit such a flat lift to the sphere spectrum?
That's a very interesting question. So I have some ongoing little project where I've mostly finished the proof. I just haven't finished writing it up. That delta ring structures on pi0 of a flat S module are actually the same as, p complete, are actually the same as H infinity structures. That's something you can just compute. Where an H infinity structure is kind of the shadow of an E infinity structure on the homotopy category, right? You have like multiplication maps like this, and they satisfy the operatic composition relation up to homotopy. It's like a really badly behaved...
Well, I know what an H infinity structure is. I still didn't understand the statement, though.
Okay, the statement is, say, M is a flat S module. Then H in flat P complete. Then H infinity structures on M are the same as delta ring structures on pi0 M. And that's really weird, right? That tells you that somehow if you have a delta ring structure, the first step in some weird obstruction theory works and you get an H infinity structure, but I have no idea whether it actually strictifies to an E infinity structure. And I'm not sure what to expect because there are weird delta rings, right? The free delta ring, I'm not sure that should have a flat lift to the sphere.
If M is a connective, what is flat?
No, flat includes connective. Flat in this sense, right? It asks also for pi-1 and so on to be just base changed. So Right. Yeah. I think we're already in the questions. So.
So questions are for Hans, for him?
Yeah.
Do you expect this relative prismatic homology to have like a Kuhn theorem?
No. So the prismatic cohomology relative prisms, that does have something like that. But if you look at this from the prismatization perspective, that essentially comes from the fact that in this prismatic situation, the prismatizations are always affine. So for such a delta pair, we can actually construct something like W card R relative A, which you have to make sense of derived in general. But that's some kind of derived stack that always sits over W card. And there is a Kuhn theorem in the sense of if you pull back two of those over W card, then you get the thing for the tensor products. What makes a Kuhn theorem hold on the level of global sections, however, is exactly that in the prismatic case, these are affine.
So you didn't say much about the construction of your theory, or did you?
I sketched that, yeah, I didn't say much. I think I sketched up there that you could do it with some absolute prismatic site, some prismatic site of delta pairs. That has some technical difficulties because you need some conditions for the psych-theoretic definition of prismatic cohomology to coincide with the derived one. And so actually, the definition we actually use, that I didn't want to get into in the talk, is that we produce a quasi-coherent sheaf on this stack, this Cartier-Witt stack W cart. To produce such a quasi-coherent sheaf, since this guy is covered by prisms, it suffices to produce something that's called like a prismatic crystal. You have to assign something to every prism in a way compatible with base change. And that we just do by something like this, where you might need to put in some completions here. Right, so if you have a delta ring A and a prism B, A tensor B is still a delta ring and inherits a prism structure from B. And R tensor B bar, where B bar is the quotient of B by its ideal, is a B bar algebra. So this makes sense in the sense of relative prismatic cohomology. And so this defines a quasi-coherent sheaf on W cart. And our definition is actually derived global sections of that. But then it's actually most of the properties I've discussed are then easy. The hardest part is then actually to see that in the prismatic case, this still just agrees with this, with prismatic cohomology R relative A. But that's the actual definition. We write down some quasi-coherent sheaf on W cart and take cohomology of that.
In some cases, it is given by a site.
Yes. So what was the exact condition? Something like R needs to be quasi-symptomic over A, I think, is the condition. Then it can be computed by global sections on that type of site. Yeah. Yes, that's exactly the technical difficulties that I mentioned that make it much easier to just use that we already have a derived version of relative prismatic cohomology and the stack W cart, and you can just work with that.
Yeah, I just want to make one little comment. I mean, first part is, I mean, the Lat theorem actually holds slightly more general. You don't need SLAD, you need what's called a Moore spectrum. Like a spectrum whose homology just sits in a single degree. And I just to address Dustin's comment, I think I want to lay this down as a challenge. Produce any delta ring where you can prove it doesn't live to the sphere. We don't know a single one, and specifically the free one.
Yeah.
And this is like a little bit shocking. So for the free one, you think it doesn't live, but I mean, this question has been studied a lot in homotopy theory. It's about the question of highly structured multiplications on Moore spectra. And I don't know.
Did you try asking Robert?
Yes, of course. Yeah, I mean, we proved actually, I mean, like in a joint project with Ellen and Shachar, we proved that somehow, actually for a lot of these lifts, actually can compute the mapping space, the E-infinity mapping space, and that ends up being discrete and just sort of a set of delta ring maps. So somehow it's not completely outrageous to think that these categories are not too far from each other. But you can also prove examples like where zero extension where the mapping space grows out of control. So it's a very interesting question, I think.
And I think that the counter challenge is produce a flat lift of the free delta ring. I think if you do that, then I'm convinced that all of them should lift. I don't believe that this guy lifts.
No, that's a way to pose a challenge.
I think we can prove that not everyone can lift abstractly.
You mean not every mathematician?
Not every delta ring.
Oh, really?
Not every.
I mean, at least not. Yeah.
You can show that some delta rings don't live.
I think you can abstractly prove that not everyone can lift functorially or so.
Okay. But here, what is the better conditions than flat? You said that.
You can ask, instead of this flatness condition, you can just ask that if you take this SA and you tensor it over the sphere down to HZ, that this is just A concentrated in degree 0. That's what Thomas meant when he said Moore spectrum, right? It's a spectrum whose homology is concentrated in degree 0. And that's slightly more general than flat because it doesn't ask for pi 0 to be a flat ZP module, right? But flatness is equivalent to this, like to the base change to HZ being discrete and flat then. So you just drop the condition that pi 0 is flat.
So I have a question. So how do, in your theory, you have a filtration. How do you see that filtration in this comparison theory?
Right. That's a bit indirect because somehow these comparison theorems, what they really get at is the Nygaard filtered Frobenius twist. There's not really a natural thing in topology that relates directly to not Frobenius twisted prismatic cohomology. The Nygaard filtration, that's just the filtration that TP has from being Tate S1 of something. And in some cases, there is actually a way to produce from this something that directly relates to not Frobenius twisted prismatic cohomology, namely if A is a prism and R is an A mod I algebra, then from this comparison stuff, we actually know that THH A mod I relative this SA satisfies some kind of Böckstedt periodicity. This is like sum of I to the n mod I to the n plus 1 shift to n. This is what Thomas and I call the ultimate form of Böckstedt periodicity. And in that case, maybe assume that I is principal. There's like a twisted version you can make instead. This is really polynomial. And then you can ask for an element U in Nygaard bigger equal 1 of Frobenius twisted prismatic cohomology. So this somehow lives in TP, which lifting a generator, like this Böckstedt class generator of I mod I squared. And then if you invert that element, you can check that this Nygaard filtered Frobenius twist actually turns into the Hodge-Tate filtered, just in a way compatible with the filtrations into Hodge-Tate filtered non-Frobenius twisted prismatic cohomology. So if you have a specific element in TP that relates to these Böckstedt elements, then you can invert that, and then the Tate filtration turns into the Hodge-Tate filtration on non-Frobenius twisted prismatic cohomology. In general, I don't really know. I mean, you can certainly descend and then left-Kahn extend from that case, but yeah, there's not really a direct description of the non-Frobenius twisted version from topology, I think.
So to make sense of this TP, do you additionally need some like some Frobenius lift of SA that refines the Tate Frobenius?
Right, I think that's related to what Dustin asked about. So it turns out so I didn't get into where this delta ring structure on A comes from. It comes from the fact that you always have this E infinity Tate valued Frobenius for any E infinity ring spectrum. But in this flat case, this actually agrees with the P completion. And so that gives you some endomorphism, which is compatible with the cyclotomic Frobenius on relative THH and so on. So that shows up. And that's the Frobenius that on pi0 actually induces this delta ring structure on A.
So does this isomorphism also hold for more spectrum?
Yes.
So if there are no further questions, let's thank Achim again.